skeletal muscles, cardiac muscle, and smooth muscle, which also represent electrically excitable cells capable of generating action potentials. So what we are going to talk about in this lecture is mainly about the role of calcium channels in the mechanism of action potential generation. I already hinted in my previous lectures that this type of channels, voltage-gated calcium channels, play an important role in muscle cells. In neurons, they are not that important for propagation of action potential, for generation of action potential, but they are important for synaptic transmission. So these channels are universally important players in the mechanisms of electrical excitability. At the end of this lecture, you should be able to describe the mechanism of action potential generation in cardiac and in smooth muscle, describe mechanisms by which action potential triggers contraction. And this process is called excitation-contraction coupling, how electrical activity is coupled to contractile activity. We will be talking about the role of gap junctions, or electrical synapses, between muscle cells in smooth muscle tissue and in cardiac tissue. This is something that is much more important in muscles compared to neurons. And finally, we will highlight the differences between two types of muscle in terms of excitation-contraction coupling, smooth muscle and cardiac muscle. What's this commotion? If you want to understand this, you have to pay attention. Okay? And you have to be in time for your lecture. Okay, so here's what we are going to talk about. You already learned about skeletal muscle, and you learned about structure, that these muscles show striation pattern. They have cross striations across the cells, and these are due to what? Why do we have striations?
Myosin and actin.
Yes, actin-myosin arranged in a regular pattern of sarcomeres, and that gives you different absorption and diffraction of light. So when you look at the muscle in light microscope, you see this kind of striations. So this is true for skeletal muscle, and this is true for cardiac muscle. We have striation pattern in cardiac muscle, but not in smooth muscle. So this is a fundamental difference, lack of sarcomeres, which involves fundamental differences in excitation-contraction coupling between these two groups, striated muscles, which includes skeletal and cardiac, and large group of heterogeneous types of muscle, generally known as smooth muscle. Smooth is because there is no striation. The appearance looks rather smooth compared to striated muscle. That's the only difference in appearance. However, there is much deeper difference in mechanisms regulating contractility, regulating electrical activity of these different muscles. This muscle, myocardium, is obviously in the heart and nowhere else. Smooth muscles are in many different organs. You may remember from anatomy that smooth muscle form the walls of all hollow organs in human body. So for the example, I put GI tract here, and every single region of GI tract, colon, intestine, stomach, has the same structure of the wall, muscular structure composed of two layers, circular and longitudinal. But that's not only found in GI tract, but in many other organs, in urogenital tract, in practically all hollow organs in human body, but also in unusual places like in the eye, regulating the diameter of a pupil, smooth muscle contracting and relaxing, and that gives different diameter, regulate amount of light coming into our eye. So this type of muscle is important for many different functions. And approximately 1/2 of these smooth muscles can generate action potentials in response to current passing through the membrane. The other half are electrically non-excitable. They may be polarized or hyperpolarized depending on inputs, but they do generate action potential as we know. And these are called non-excitable, and they are found mainly in the vessels. And in some parts of GI tract where we need a tonic contraction, constant, long-lasting contraction. For example, in sphincters. This may maintain long time contracted state, then relax to pass food bolus further down, and then contract again. So depending on their function, cells may lose the ability to generate action potentials or acquire that ability. And that is all governed by the presence of different types of potassium channels. In non-excitable cells, there are voltage-gated channels, but potassium channels are predominant. So they clamp membrane potential on the resting level so much that any current passing wouldn't generate action potential. It may be polarized, calcium channels may open, and there will be long entry of calcium, and that creates contraction, as you will see in a moment. But they don't generate action potential. And so for now, let's consider differences in structure of actomyosin between smooth muscle and striated muscle. Remember, this is representative for skeletal muscle and cardiac muscle. And there is a fundamental difference in the arrangement. Here we have very regular structure, which is repeating itself every 1.8 to 2 microns, and the structure is called sarcomere. It's called so sarco because of Greek word for skeletal muscle, but as I said, it is found in cardiac muscle as well. So it's a regular structure, and the way it generates force is by interaction between myosin fibers and actin fibers by creating cross bridges, and cross bridges pull, exert force, so the muscle eventually tries to contract due to interaction between actin and myosin. In smooth muscle, force is also generated due to actin-myosin interactions, due to force generating cross bridges. But the way they are arranged is substantially different. Instead of regular sarcomere, we have much shorter, smaller, thick filaments, myosin filaments, which are connecting actin filaments, shown in blue here. Okay, and they are interacting with 2 of these filaments, similar to what happens in the sarcomere. However, because there are many of them in one direction, and these directions are crisscrossed through the muscle, when the muscle contracts, it may assume much shorter form compared to the relaxed length. And that's how the smooth muscle can stretch or can shorten to accommodate different sizes of the cavities. For example, stomach. In unfed state, in fasting state, the size of the stomach is pretty small. And then as we eat, it relaxes and becomes bigger. Pressure isn't changing very much. You will learn about it in due course, in more detail. But I can tell you now, the pressure is not what stretches the stomach. the ability to relax and accommodate a lot. And then when we need to pass it to the duodenum for further processing, the smooth muscle contracts and insert pressure and push food down the GI tract. So this makes functional sense, this kind of arrangements. And the bonus, additional bonus of this type of arrangements is that if you leave that muscle untouched, unloaded, as it is, at rest, it will assume certain lengths and it will stay at that length. If you apply a little bit of force, of course you will measure some kind of resistance, but that resistance goes away. Why? Because of rearrangements here. And when contraction happens, all the filaments, actin filaments, slide along myosin and make it shorter. So the muscle can change its length very easily and to large extent, much larger extent than skeletal muscle or cardiac muscle. And that is dictated by the functional requirements. Now, let's talk about action potentials. We learned neuronal action potentials, and you talked about skeletal muscle action potentials in the previous lectures with Dr. Sandeep. If you compare duration of neuronal action potential with cardiac action potential, you will see that the whole duration, including graded potentials, synaptic potentials, and then threshold depolarization, repolarization, and residual after hyperpolarization, all together last much shorter than one single action potential in the cardiac muscle. So cardiac myocytes generate very long action potential. If neurons generate action potentials lasting from half a millisecond to a couple of milliseconds in different fibers, different durations, but everything is within 2, say 3 milliseconds, then these ones are about 300 to 400, 500 milliseconds, so pretty long. And that increased length is due to the presence of different types of ion channels and different conditions of the functioning. So instead of just depolarization and repolarization, we have a few more phases here. Phase 0 is pretty much similar to the phase of depolarization. And then we have a partial repolarization, initial fast repolarization, phase 1. And then slow repolarization or plateau. And that's distinctive feature of cardiac muscle and some smooth muscles. You don't see plateau in neurons or in skeletal muscle. And this is followed by final rapid repolarization and resting phase, phase 4. This is phase 4, this is phase 4, resting potential between action potentials. Okay, so as I said, these different phases are due to the functioning of different ion channels. So before we go into details, let's take registration and then talk about cardiac action potential.